This video is going to embrace your talent and hope you guys use them as a springboard for the further development. Here, the first and the foremost thing is this topic is from Integration Using Residues, and this is of the type integral minus infinity to plus infinity e power I mx into f of x into dx. Now, in this video, I am going to prove that integral minus infinity to plus infinity cos ax by x squared plus 1 dx is nothing but pi times of e power minus a, where a is greater than or equal to 0. So here is the solution. So as you know that e power I theta is nothing but cos theta plus I into sin theta. So here in place of theta we have ax. So here e power I into ax is nothing but cos ax plus I sin ax. So I need cos ax. So this is from the question. So what will be cos ax? Cos ax is nothing but the real part of e power I ax. See clear? Cos ax is nothing but the real part of e power I times of ax. Now I am going to consider the function. So that is integral c f of z into dz is nothing but e power. So the real part of I times of az by z squared plus 1 into dz. So here what is this c? C is nothing but, so c is nothing but a semicircle. So as you know that c is a contour consisting of a semicircle CR where mod z is equal to 0. So this means, so this is z minus 0 is equal to r. So this is a semicircle with center 0 and radius capital R together with the bounding diameter minus RR as shown in the figure. So this is the figure shown. So this is a semicircle with center 0 and here is the radius. So this is the radius capital R and this is minus R to plus R. So from the real axis minus R to plus R. So this is the total closed contour. So the journey starts from minus R to plus R and again through the semicircle CR with center 0 and the radius r. Therefore, the total integral c f of z dz can be written from minus capital R to plus capital R, as this is the real axis f of x into dx plus cr. Cr is nothing but a semicircle with center 0 and radius r into f of z into dz. So, the integral is split into two line integrals. One is from minus r to plus r and next one is the boundary line for CR semicircle from mod z is equal to r. Now what we have to do? So in order to solve this, we have to find the poles. First of all, we have to find the poles. How we have to find the poles? So here is the function. After considering this as a function, as you know that in order to find the poles, what we have to do? So we have to equate the denominator to 0. So what is the denominator here? So this is z squared plus 1 is equal to 0. So z squared will be minus 1 and z is equal to root over minus 1 and z is equal to what is? Minus 1. So this can be written as I square and z value is equal to plus or minus I. So these are the poles. So these are the two poles, simple poles. Z is equal to plus 1 and Z is equal to minus 1 are the two simple poles. And now what we have to do? So minus I and plus I are two simple poles. And the next thing is we have to check whether these poles are within or on or inside the given contour. So what is the contour here? As you know that the contour here is nothing but a semicircle. So this is from minus r to plus r. The journey starts from minus r to plus r and later through the semicircle with center 0 and radius capital R. So this is mod z is equal to 0. So this is CR. See here, now we have to check whether these two poles lies within or on or outside the given contour. As you know that, so this will be plus I and this will be minus I. As it is very clear that plus I is within the contour and minus I is outside the given contour. So after that what we have to do? So we have to find the residues for the interior poles. For finding the residues of the interior poles, what we have to do? So here is a simple formula, that is the residue of f of z at the interior pole z is equal to I is nothing but this is limit z tends to I. This is z minus I into f of z. So we know our f of z is ready, that is limit z tends to I. This is z minus I into f of z. So what is our f of z here? It is very clear as e power So this is e power I times of az by this value is z squared plus 1. Z squared plus 1. Now this will be limit z tends to I. This is z minus I into e power I times of az by z squared plus 1 can be written as this is z plus I and this is z minus I. Now easily we can cancel these two and substitute in place of z as I. So what happens here? This will be e power IA in place of z as I by this value is going to become I plus I. So as you know that so a times of I square is nothing but minus 1 by this is 2I. Clear? So this is nothing but the residue of f of z. For the interior pole z is equal to I. As it is very clear that the residue value for the interior pole z is equal to I is nothing but e power minus a by 2I. Next what we have to do? As usual, so after finding the residue, so here is the residue value. This is the residue value of f of z. For the interior port, z is equal to I as e power minus I by. So this is e power minus I by, this is 2I. So later we have to substitute this in the residue theorem. So what does the residue theorem statement states? The residue theorem statement states that, so according to our residue theorem, so this is integral C f of z into dz is nothing but this is 2 pi I times of sum of the residues at the interior poles. So what is our interior pole? So interior pole is nothing but z is equal to I. Therefore, our question here will be, so this will be integral C f of z into dz is nothing but this is 2 pi I times of the sum of the residues at the interior pole is nothing but e power I times of az by this value. See here, sorry, this is e power minus a by 2I. So this is nothing but e power minus a by 2I. And now see, this will be integral C f of z into dz value is equal to, this is 2 pi I times of e power minus a by 2I. And now we can cancel 2I here and 2I. And what remains here? This will be integral C f of z into dz value is equal to pi times of e power minus a. Then what is our closed contour C? As you know that our closed contour C is nothing but a semicircle. So this is nothing but a semicircle from minus r to plus r. And see here, this is 0 to r. So the journey starts from minus r to plus r and later through the semicircle. This is a CR which is equal to mod z is equal to r. Now our total contour here is, so this is our total contour. So in this, our integral value will be, so this integral value will be, so the total contour value will be, this is minus r to plus r. So minus r to plus r, as this is real axis, f of x into dx plus. So this is the border line, that is a CR. So which is nothing but f of z into dz value. The value here is pi times of e power minus a, and this is equation number 1. And now as r tends to infinity, so here as r tends to infinity, what happens here? So this can be written as integral minus infinity to plus infinity f of x. So here f of x is nothing but e power iax by, so this is x squared plus 1 into dx. As our f of x value is very clear from the question, as see here, as our f of x value is nothing but this one. So in terms of z I am writing a, that is e power iax by x squared plus 1 into dx. So this is f of x value plus, so this is a CR, f of z into dz value is nothing but pi times of e power minus ia. Now as here r tends to infinity, so what happens to this integral? So I am going to check. See here, it is very clear, CR by f of z into dz value is equal to, this is CR, f of z value is nothing but e power iaz by, this is z squared plus 1 into dz. See, I'm giving you a clarity here as we have to put z value as. So put z is equal to r into e power I theta. See what happens here. If you keep r into I theta, take modulus. Modulus of z value is equal to modulus of r into e power I theta. As you know that modulus of e power I theta is nothing but modulus of cos theta plus I sin theta. See here, mod z is equal to, clearly this value is cos theta plus I sin theta, and mod z value is equal to, this is root over clearly cos square theta plus sin square theta. Therefore mod z is equal to r. So this value mod z is equal to r. So please remember this one. And the next one here is I need dz value. As you know that z is equal to again r into e power I theta. See here, dz, the derivative for this is, for e power I theta is again e power I theta, I times of d theta. Now if I apply modulus, so this will be r e power I theta, and this is mod I into dz. So clearly dz, mod dz value is equal to r times of, here the same thing runs, cos theta plus I sin theta, which is equal to root over cos square theta plus I sin square theta. This is 1, and this mod I can be written as, see, mod I can be written as 0 plus I times of 1. So if I take modulus, this will be 0 square plus 1 square, which is equal to 1. So into d theta. So here mod dz value is also ready. So here is our problem, that is integral C. So if I take modulus, that is a CR, modulus of e power I a z by, so this is z square plus 1 into dz. So this value is less than or equal to integral CR e power I a z by, this value is r square plus 1, and dz value is nothing but r into d theta. So this is r into d theta. So this value is less than or equal to CR r by, this is r square minus 1. So this is even less than or equal to r square minus 1 into e power iz. So this value is cos az, cos square az plus I sin square az, this value is 1, and this is going to be as r tends to infinity. So this is r. If I take r common, this r square common, this will be, see here, this will be 1 minus 1 by r square into, here this is d theta, as r tends to infinity. Here in the denominator r remains, this is 1 by infinity, which is equal to 0. So this is tending to 0. So which value is tending to 0? Integral CR f of z dz value is equal to 0 as r tends to infinity. So this is the clarity. So this is the substitution. We have to substitute r is equal to e power I theta. And next thing here is, after taking modulus, so 1 by r remains, as r is tending to infinity, 1 by infinity value is 0, as this value tends to 0 as r tends to infinity. So this is the clarity which I have given. For this CR, so this is going to become 0 as r tends to infinity. Therefore integral minus infinity to plus infinity e power ax by, this value is x square plus 1 into dx value is clearly pi times of e power a. So what is e power ax? So e power ax, if I split this one as, this is cos ax plus I sin ax. See here, cos ax plus I sin ax by x square plus 1 into dx, and this is pi into e power minus a plus I times of 0. So if I equate the real parts, equating the real parts and neglecting this one, imaginary part, this will be minus infinity to plus infinity cos ax by, this is x square plus 1 dx value is going to become pi times of e power minus a. So this is how we have to solve, as this is real part and this is imaginary part. If I equate the real part from the both sides, so this is our real part and this is our real part. If I equate these two, then our minus infinity to plus infinity cos ax by x square plus 1 dx value is nothing but pi times of e power minus a. So this is what it is asked to show that, and this is also so simple if you follow these steps. This is integral minus infinity to plus infinity cos ax by x square plus 1 into dx is equal to pi times of e power minus a. So first of all, it is Well known that e power I theta is nothing but cos theta plus I sin theta, and we need cos ax, and cos ax is nothing but the real part of this one. So after considering f of z like this, and this is the contour C, so contour C is from the real axis minus r to plus r, and again the border line from mod z is equal to r. So this is the contour. So the contour is split into two parts, and the next thing here is we have to find the poles. After finding the poles, so we got the two poles as plus I and minus I are the two simple poles, and plus I lies within the contour and minus I lies outside the contour, and this is how we have to find the residue for the interior pole. So this is the value, this is the residue value for the interior pole, and after finding the residue we have to apply in the residue theorem. So this is the residue theorem. So this is 2 pi I into the residue value here. So we got this one. As you know that the given contour, closed contour, is split into two parts, and now we have to find out the value of this second integral as r tends to infinity. So as r tends to infinity, I have given a crystal clear clarity for how this is becoming 0. So after substituting this value as 0, so this will be the answer. And see here, I'm writing this as e power I theta can be written as cos theta plus I sin theta. So equating the real parts, so we got the final answer as e power minus infinity to plus infinity cos ax by x square plus 1 into dx is equal to pi times of e power minus a. So thank you so much for watching. As you know that I have given clarity for each and every step so that you can understand and you can solve by your own, and you can spread it to so many friends and your well-wishers, siblings, everyone, and hope you spread this knowledge. Thank you so much for watching and staying till the end.